Well, I hope that last discussion about analytic solutions to Laplace's Poisson's equation has convinced you of a few things. Firstly, we've got these method of images that can solve a small number of problems. We've got separation of variables, can also solve a small number of problems. The method of images can be relatively quickly, but it's very limited. The separation of variables can solve more problems than the method of images. It's still quite limited, but it's also quite a lot of work. We're now going to look at the numerical solution of Laplace's equation in some region of space based on the boundary values of the electrostatic potential at the edge of that region of space. So we're going to now study the numerical solution of this type of problem. So if you look in this problem here, looks similar to the last problem, not quite the same as the last problem. I'm imagining a square box. So the red and the blue lines are the walls of the square box. I'm imagining they're conductors. The lower conductor is at a fixed positive potential phi naught. The left, right, and top walls of the box are grounded, so it's zero potential. And we want to solve for Laplace's equation everywhere inside the box. We want to find the electrical potential everywhere inside this box. And now we're going to do this numerically, and we'll see how straightforward, simple it is to do numerically. So firstly, I want to outline the key ingredient in solving this problem numerically. And that key ingredient is really to replace the partial differentials, or to approximate the partial differentials as difference equations, differences in the potentials between neighboring locations. And then once we've done that, I'll discuss our computer program, which uses these difference equations to basically iterate and reiterate to find the electrostatic potential inside the box from some sort of guess, some sort of arbitrary guess of the electrostatic potential in the box. So we'll see how that works out. But let me start with the approximation of the difference equations for the partial derivatives. This is all based on something that we've already met, which is the Taylor expansion. If you remember back to the Taylor expansion, because I'm not going to write down the Taylor expansion again, it was a way of writing down the value of a function, let's call it f, at some location, let's call that x, so f of x, in terms of the function's value at some other location, say f of a neighboring location, say f of a, and the slope at that location, so the first order differential at that location, the curvature at that location, so the second order differential at that location, and so on and so forth. So it wrote f of x in terms of f of a and its differentials. And it was a series, right? In principle, it's an infinite series of terms of higher and higher orders of differentials that make smaller and smaller contributions. Well, if you think of that Taylor expansion, it contains the second order derivatives. And we're all interested in the second order derivatives of the function here. We're interested in the second order derivatives of the potential. And actually, you could, if you take the Taylor expansion for a series of neighboring points, you can rewrite that Taylor expansion for a series of neighboring points as an expression for the second order differential at the center of that arrangement of points. So let me get specific here. We want the second order differential of the electrical potential with respect to X. We want the second order differential of the electrical potential with respect to Y. I'm going to imagine we want the potentials at some point X, Y that I've labeled in green here. We can write those potentials at this point, these differentials of those potentials at this location X, Y, in terms of the values of the electrical potentials at the neighboring point. So in this top equation here, when we're thinking about the partial differential with respect to X, you see the potential at XY, so that's the green point, and you see the potential at the neighbors to the left and to the right. And when we want the potential with respect to Y, you see the potential at the location XY, so the green point, and then you see the potential at the two neighbors above and below, upstairs here and downstairs here. Basically, these equations are saying you can approximate the second order differentials of the function, which measures the curvature of the function, in terms of, if you're thinking about the differential with respect to X, the value of the function at the point XY and the values to the left and right of it. And if you're thinking about the differential of the function with respect to Y, the value of the function at the point XY and the values of the function above and below it. So this is this approximation. If you take these two equations, you can plug them in to Laplace's equation. So Laplace's equation is simply the sum of these two second order partial differentials, and that sum of the two second order partial differentials equals 0. And so that's all I've done here. I've replaced the second order partial differentials with the difference equations and collected together terms and canceled out a common factor in the denominator of a squared. You get this little equation here. You see it has the potential at the green point, XY. You see it has the potentials at the points to the left, the right, above, and below. That's these four different potentials here. And if we like, and this is what we're going to do to solve this problem, we can turn this equation around and say that we could calculate the potential at the location XY, the green point, based on this combination of the potentials at the four surrounding points, upstairs, downstairs, left, and right. And so we're going to use this to calculate the we're going to use this equation to calculate the electrical potential in the. So this slide shows you the basic method, the basic approach to this problem. On the left-hand side, here's the box again, and I divided it into a lattice of discrete space-time points. So I'm not going to work in continuous space. I'm going to work in these discrete space points. And so that's how we perform the numerical solution. And what we're going to do is calculate the values of the potential at each of these points, rather than calculate a function that describes the potential in a continuous manner. And we're going to use this equation from the last slide, the final equation from the last slide, to calculate the potential at XY, so phi XY, from the four potentials at the four neighboring points, the ones above and below to the left and right. And so that's going to be the procedure. And to calculate the potential at all the points, we'll just walk through the points, top row, next row, so on and so forth. And so we walk through all the points, and each time be calculating the electrostatic potential at a given point based on the potentials at the neighboring points. So that's basically going to be the procedure. So the way we start this problem, the way we start doing this, is first we fix the potentials on the edges of the grid, on the conducting plates. We fix those potentials at the boundary values. So on the top, the left, and the right, the potential 0. On the bottom, the potential's phi 0. We're going to keep those fixed. and we won't change those. We then guess the electrical potential in the interior. Now, a simple guess is actually that the electrical potential inside the interior is just zero everywhere. So let's just guess that. But we could pick other guesses too. But we're going to just pick, for our example, the electrical potential is zero everywhere, knowing that it's not zero everywhere. Knowing that that's just some simple-minded guess. And then we're going to walk through all the points inside the box, updating the potential based on this equation, recalculating the potential based on this equation, and the potentials at the neighboring points. So think about what's going to happen when you do that. Let's think about the first iteration of recalculating the potential. If you're a point in the interior, like this green point here, then the neighboring points are still zero electrical potential. You're going to recalculate zero electrical potential. So this point's not going to change. This potential is not going to change. But if you're a potential near the edge, take this point here. When you calculate the electrostatic potential at this location, the new electrostatic potential at this location, from the potentials above, below, and to the left and the right, it's no longer going to be zero in general, because it's going to be affected by the potentials on the boundary values, on the boundary conditions. And so potentials, say, for example, this point down here will start to change when you recalculate the electrical potentials. And I think you could imagine that this potential downstairs here on the lower plate, which is non-zero, each time you recalculate the potential inside the box based on this algorithm, based on this equation, this potential is going to kind of propagate, it's going to kind of grow into the box, and it's going to spread, grow through the box, and it will, with time, with iterations, get closer and closer and closer to the true potential in the box. And so we're going to calculate, and recalculate the potential inside to the box until it converges to a stable value within some accuracy, within some tolerance. This is called a relaxation method. We're going to recalculate and recalculate and recalculate until it relaxes to a constant potential inside the box. So now I'm switching to my code for calculating the potential inside the box. And this is where you get to see just how simple, straightforward the numerical method for solving Laplace's equation or Poisson's equation based on boundary values actually is, how powerfully it is compared to that method of images and the few cases in the catalog that it can solve, or that method of separation of variables and the handful of simple geometries that it can solve. So there are actually just two significant cells in my code here. This one upstairs and this one downstairs here. And it's these two cells that solve the problem. Actually, the first cell is just setting up some parameters for the problem. And then the second cell is really the calculation of the electrostatic potential for the problem. So let me just walk through these two cells. So in this first cell, M is the size of the grid of discrete points in space inside my box. So I made M, in this particular example, a lattice, a 25 by 25 lattice. So if I was to make more lattice points, I get a more accurate, a finer grid and a more accurate electrostatic potential. If I made less lattice points, then I would get a code that would run more quickly, or run more speedily. So This is where you make a compromise between accuracy, the fineness of the grid, and speed, how quickly the code runs. So I've got a 25 by 25 grid. In this particular problem, if you remember, I've got grounded plates on the top, left, and right. The plate on the bottom is at some fixed potential. V is that potential. And I've just made it 1 volt. So here's the potential on the bottom plate. Target. Target is the accuracy that I want to achieve in calculating the electrostatic potential. I want to achieve an accuracy that's a part in 10 to the 4. And so this is where I define an accuracy, and I'm going to use this in my calculation. I'm basically going to iterate and iterate and iterate in my calculation until I achieve this accuracy. And when I get to this accuracy, I'm just going to quit. And so I could, if I wanted more accurate, I'd make this a smaller number. Less accurate, I'd make this a bigger number. I got 2 phi's here, which are 2 arrays. And I'm setting them equal to 0. I'm declaring them, initializing them to 0. Initiating sounds like I'm putting them in a frat house or a sorority house, but I'm initializing them to 0. So phi and phi prime are the before and after electrostatic potentials, where before and after is before and after I update the potential at a particular location based on the potentials of the neighboring locations, based on that equation that we derived, the difference equation. So I'm just going to use these 2 arrays here. You see their size. It's the dimensions n+1 horizontally, n+1 vertically. That encompasses my entire grid, includes the boundaries on my grid. So the boundaries on the grid will be when the array elements, when array index is either 0 or is n+1. Finally here, I have to set into this, the initial potential phi, I have to set the boundary conditions. So because I define them all to be 0, the boundary conditions on the left, right, and top are already set to be 0. But the boundary condition on the bottom side of the box, I've got to set that to be V. I've got to set that to be the 1 volt. And so that's what I'm doing with this slicing here. I slice out that bottom row of elements, and I set them all to V. I set them all to 1 volt. And so that just really sets the and initializes the parameters of the problem. The second cell then is where I actually execute the problem. And let me start by discussing this section of the code here. So here you see a nested for loop, a loop over I and a loop over j, where I runs from 0 to n+1, j runs from 0 to n+1. Obviously, we know what that is. That's me walking through all the elements of the box, all the points in discrete space that make up the box and the walls of the box. So I'm going to walk through all of them. Now, in general, I want to, when I walk through those points, I want to re-update the electrostatic potential at a given point, ij, based on the potentials at the neighboring points. You know, I plus or minus 1, j plus or minus 1. So in general, I want to do that, but I don't want to do it on the boundaries of the box. So if I'm on the left-hand wall, the right-hand wall, the top or the bottom of the box, I don't want to change the potential. And so that's what this if statement is for. It just says if I'm on the left-hand wall of the box, right-hand wall of the box, top of the box or bottom of the box, I'm not going to change the potential. I'm not going to potential, meaning phi prime, the new potential, the after potential, is going to be exactly equal to phi, the before potential, the original potential. But if we're not on the walls of the box, so else, then I am going to recalculate the potential. I'm going to recalculate the potential phi prime at the coordinate ij in terms of the potentials at the four neighboring points, I plus or minus 1, j plus or minus 1. And so that's what I do here. And then I just keep walking around this loop. I just keep walking around the loop. Once I've calculated phi prime for all the points, notice here, I replace the original potential phi with the new potential phi prime and redo, walk around this loop again. And here is where I keep walking around the loop, this while statement. So this while statement keeps me walking around all the array elements so long as a quantity called delta is bigger than that precision, that target precision, that target accuracy. So what's delta? Delta's here. Delta is the biggest difference, the biggest change in phi that I got when I updated the old phi's at all the points to calculate the new phi's at all the points. And so this is the biggest change. And so I'll keep going around this, this nested for loop until that change in phi, until the recalculation of phi is smaller than 10 to the minus 4, the target precision. And so when it gets to below 10 to the minus 4, I no longer carry out the iteration. I no longer carry out the updating the electrostatic potential to get phi prime. I'm done. And at that point, when I'm done, I use this plotting function just to plot the plot the results for the potential. So let's carry this out. It's pretty quick. And this is what the potential looks like when I use this IM_show plotting function. I'm plotting the phi here. Now, one thing about IM_show, image show, it's really a function for plotting a matrix as if it was an image. One thing it does that's a little inconvenient here is it's rotated our geometry. So the bottom of the box is actually over here on the left. The left and right walls are the top and the bottom, and the top of the box is over here on the right. But look, if we look at the resulting solution, the color coding is telling us the potentials. We can see that on the conducting plate at phi 0, 1 volt, that's the yellow column here. On the grounded plates, that's the black column at the top, the black column at the bottom, and the black column on the far right. And then in between, the colors in between are the changing potential in between. And so we see how this 1 volt potential kind of percolates outwards, propagates outwards, grows outwards into the box, and slowly falls off towards 0 as you walk from the left-hand edge of the box to the right-hand at the edge of the box in this particular picture of the box. And so that's what this is the solution to our problem. Just to make it a little more quantitative, I made a second plot. So in this second plot, I'm plotting horizontally here. This is the x coordinate within the box. So this is walking from the left-hand side over here on the left-hand side of the graph to the right-hand side of the graph of the box. And I'm plotting the potential at different y locations in the box. So the first y location in red is this guy here. That's 0. And so that's the lower conducting plate, and that's 1 volt. And we set that to be 1 volt. Immediately above, the cells immediately above, or the lattice points immediately above, so that's y equals 1, is the green line here. So you see in the middle, the potential's fallen off a bit. You see at the edges, the potential's fallen off a lot. And then the blue, the yellow, the magenta, and the azure, these four correspond to potentials actually at location 5, 10, 15, and 20 in Y. And so that's the values of these. That's the potentials across the box at these different vertical heights as we basically walk up the walls of the box. And so that shows you in another way how the potential is changing. I want to show you as a final comment or remark about how flexible, how powerful this numerical method is for solving electrostatic potentials based on boundary conditions. I'm going to add to the box, inside the box, I'm going to add a wire, a conducting grounded wire at a particular location in X and Y. So imagine it running along the length in Z. It's at a particular location in X and Y. I'm going to ground that. I'm going to put that at 0 volts. That's going to change, in general, the potential everywhere inside the box. And I'm going to recalculate the new potential with that wire. That would be a very hard problem. That would be an impossible problem by separation of variables, by method of images. That's only possible by solving this type of problem numerically. So all I've got to do is add a few lines of code to do that. I've got to add a line or two of code to specify where my conducting wire is and the potential of my conducting wire. And then I've got to slightly modify the code where I iterate the electrostatic potential, because now I not only don't want to change the potentials on the walls of the box, but I don't want to change the potential on the wire. So let's see how that works. So firstly, in this first cell, I'm going to add these two lines. So the first line specifies the XY locations, or the IJ locations of the wire. So it's roughly in the middle of the box, horizontally. It's at the lower edge, towards the lower side of the box, vertically. That's the coordinates 12 and 5. And then I'm going to assign the value of the potential at that location to be 0. So I'm going to ground that location. So those are those two lines that I've added to this first cell that initializes the problem. In the second cell, this is where I carry out the calculation of the electrostatic potential by iterating over the electrostatic potential. I need to add two lines here. In addition to avoiding changing the potential on the left, right, top, and bottom walls of the box with this statement, this if statement here, I also want to avoid changing the potential at the location of the wire. So if I and J are equal to the location of the wire, then I'm also not going to change the electrostatic potential. Phi prime is going to be equal to phi. So that's my only change in the code. So let's run the code again. And let's look at the solution now. And here's our grounded wire. So this point here is now 0 potential. And this grounded wire here has affected the potential, especially in the neighboring region. So it's changed the potential in this region here quite dramatically. We can see it perhaps more clearly if I look at these horizontal projections of the potential. So here's the bottom plate. Here's the region of space just above the bottom plate, the row of points just above the bottom plate. You see at the center here, small influence of the potential due to the wire. As we walk further up the box, remember we're walking up to Y locations of 5, 10, 15, 20. Look at 5. This is where we put the wire. Now you see there's a dramatic change of the potential here due to the influence of the wire. You also see the change at y of 10, but that change kind of goes away, disappears away as you get further and further up the box. And so this shows you how that conducting wire, that grounded conducting wire, has changed the potential inside the box. Anyway, I hope you see there that the numerical solution of the electrostatic potential, numerical solution of Laplace's equation based on boundary conditions, is actually really rather straightforward, really rather simple to implement. And we've been able to quickly write some code and execute some code that solves a problem in the first case, though it would be complicated to solve by separation of variables and applying the boundary conditions, complicated to solve analytically. And in the second case, with the conducting wire, would be impossible to solve with separation of variables and applying the boundary conditions. And so this is a very, very powerful technique. It's used a lot in research. Often in research, you have to compute the electrostatic potential of the electrical field in some device, in some instrument, and there are programs, professional programs, that use these types of methods to solve that electrostatic potential, solve that electrostatic field based on boundary conditions. And so this is our first introduction to this.